Just isn't it okay? Del F evaluated x, y as a vector, right? So let's just do our favorite function, my new favorite function, okay? 2 square root of x, y. Well, del F equals this applied to the function. Okay? Now you can always pull out constants because we're just doing derivatives. So I'm just going to pull out the 2. And then the partial with respect to x of x, y. Actually, I'm not going to pull out the 2. I'm just going to do it. Okay, it's a square root of y over x, I, plus the square root of x over y, j. Okay? And you can verify this very easily. I mean, you just do this partial with respect to x is y, square root of y over x. Partial with respect to y is x over y. And you did that for homework. You used it in homework, which is why I'm using it now. Okay? For any function, that's what you have. Okay? So, it's that is a vector, isn't it? And we can say it's a vector. Actually, del F is a vector function, but when you evaluate it at a point, it becomes a vector, right? Okay? So, del F evaluated at the point 3, 5 that we used is what? It's going to be this. I mean, just plug it in for x and y, that's true, okay? Okay? So, this is a del F evaluated at a specific point, right? Okay? And let me say, let's call this x naught, y naught, because that's what we often do when we want to talk about a specific point, okay? Give it a couple of subscripts as opposed to the general variable point x, y, okay? Now you do the gradient on the variable point. You don't plug in the specific coordinates because then you just have a constant and your derivatives are all going to be 0, right? So that's one thing that, you know, people sometimes tend to do that. I haven't seen you guys doing that at this point, so I don't think that's going to be a problem. But I thought I'd mention it. Okay, so anyhow, that's a vector. That has some really neat properties. Its direction is the direction in which f changes, in which f increases most quickly. Okay? Now there are analogies to walking on a hillside. I'll just mention, if you're on a hillside, well, that hill is a function of 2 variables. Z is your altitude, x and y is your position on a plane. Okay? Well, your direction of maximum increase is easy. That's the direction you go if you want to get up the hill fastest. Assuming it's not so steep that you slip off of it, right? So assuming it's walkable, if you want to get up as fast as possible and you don't have injuries that prevent you from going in that direction, you go in that direction. Okay? That's the gradient. So if you imagine a quadric surface, walking along the quadric surface, the gradient of the function that gives you the quadratic surface, x squared minus y squared, or whatever it is, or square root of xy, okay? Tells you the direction that you go to go uphill as fast as possible, okay? Another thing that I'll mention now, and we'll write it out carefully, maybe before we're done, but we've only got 9 minutes, and maybe not, okay? If I want to stay on a level, okay? So if straight uphill is in this direction, what's the direction in which I'd stay level? What's the direction of the cow paths on the side of that hill? Perpendicular to the direction of greatest increase. If you're walking along a path where everything is level and you want to go uphill as fast as possible, you turn 90 degrees, hopefully to the uphill side, and walk in that direction, right? If you want to go downhill as fast as possible, you turn 90 degrees this way. Okay? So that's worth, that image is totally related to what we're doing here. Okay? Okay, well, so that's why this is important. It tells you two things. It tells you the direction of maximum increase, and it also tells you the direction where your function doesn't change, which is perpendicular to your direction of maximum increase. In this case, perpendicular at the point 3,5 to this vector. Okay? Okay. See how long this thing's getting. I'm a little long-winded today. Okay. Make sense? At least tentatively? You get the image?
Yeah, a little bit.
Okay. So I can say and perpendicular to the direction of no change. Okay? Well, this direction square root of 5/3, right? I think somebody told me it was 1.28. And this is like 0.79 J. Okay? And the unit vector is this over its magnitude, right?
How do you know that's the direction of max increase?
Because I said so.
So
We don't have time to prove it today. We will next time. And you can look at your book. You just maximize fx cosine theta plus fy sine theta. You find that that expression maximizes for theta in the direction of the gradient. That every directional derivative you get will be less than this, and that this is the maximum, okay? And you just kind of write it out. It's not a difficult thing to prove, but you know, we're down to 5-6 minutes now. So I'm not going to prove it today, okay? Not going to prove any of this stuff. As I said, I'm telling you about it, and then we'll put it on a firmer foundation. But you can do these calculations. If I give you a function and ask you to find the gradient, as long as you can do the derivatives, which you can, you're going to be able to do it. If I ask you to give me a unit vector in the direction of maximum increase, what are you going to do? You're going to calculate this, right? And then you're going to divide by its magnitude. Okay? And the unit vector is going to be this over the square root of 5/3 plus 3/5, as you can easily verify. Because the square of the square root is a fraction. You can add that and get the exact result. Take the square root on that. Now you can't see the 3, but you know what I wrote down. Okay? Nothing to it. Also, of course, then, what you get when you divide, simplify the I component, or just isolate the I component, take its inverse cosine, and you've got the angle theta. So you know what the direction is, okay? So you do all that. So, you'll have exercises that build these fairly easy skills. So you can put all this into a picture, okay? Okay, so anyhow, in the direction of no change, this thing has a slope of this over this. Perpendicular to that has a slope of negative this over this. So your direction of no change is going to be, I'll even do a unit vector. It's square root of 3/5 I minus the square root of 5/3 j over the square root of 5/3 plus 3/5. And you can also, just by inspection, see that if I do the dot product of this with this, I'm going to get 0. So you don't even have to think negative reciprocal slope. Just find a vector whose dot product with this one is 0. Now when you get into higher dimensions, you use some other techniques, okay? But in 2 dimensions, that's easy. So now we know this about this function at the point 3,5. If you want it at the point 5,3, because one we did in class last time, the other I assigned, you got everything you need to get all this information about this function. Okay? And you've already calculated its tangent plane at that point. So you're getting all kinds of information. And you can do the same thing for any function. Well, so, perpendicular to the direction of no change. And what more can you say about the gradient evaluated at that point? And this. Okay? So, square root of 5/3 plus 3/5. And that's easy, okay? That's 25 and 9/34 over 15. And that's pretty close to 1.5. Okay? Certainly within a tenth, and I think maybe it really is to the nearest tenth, it's maybe 1.5. Certainly more than 1.4, because that would be 30 over 15, right? Might be as much as 1.6. I don't think it's as much as 1.7. Okay? And I haven't even thought about it. It's just totally intuitive visualization. Okay. So, make sense? Well, it's not difficult to do these calculations. Not difficult to get used to doing these calculations. And actually using them to draw conclusions about this function or any other function, okay? There's a lot of material here that goes all the way back again to your parallelepiped, okay? And you want to connect it all the way from a parallelepiped up to these properties. Hopefully by Tuesday. But, it takes a little time to process. To start on it earlier, it'll take you longer. You might get it done by Tuesday, but whether it sinks in, you don't want to wait till the last minute if you can help it. This is a big, big, big deal.